Good. So we have our next speaker, who's Mattia Cenedese from ETH Zurich as well. Perfect.
Thank you, and good afternoon, everyone. My name is Mattia Cenedese, and today I'm going to talk about modeling and prediction of non-linearizable phenomena via dynamics-based machine learning. And this is joint work with experimentalists and co-developers and also supervisors that you see here. So when we look at dynamical systems, in reality, we have examples here like structural dynamics and fluid dynamics, interactions, and so on. They often have two main issues, namely, the one is high dimensionality, so it takes a long time to simulate or to do experiments, and then no linearities. And with respect to statics, another issue we have that we look at time series, not at single outcomes that we have. And our goal here is to develop predictive modeling and needs to be a reduced sorter, also eventually, of non-linearizable dynamics that then can be used for prediction and control, for identification and control. And you see here some phenomena like limit cycles and force responses and complex fractal type basis of attractions, turbulence. These are all fundamentally non-linear, and they have some complexity inside. And there has been a great push into research into develop this kind of models by looking at the data. And there are many algorithms that have been developed, but there are some, we saw some issues in here. First of all, some of them cannot return physically admissible models, or some others can assume just a sparse model, but where is the sparsity guaranteed? Why, if it depends to the coordinates that you're looking at. Or some of them have problems in making predictions outside their training range, or other needs also to observe the full phase space, not just one particular observable, which is the typical case if you think about structural dynamics, for example. This is why we take an approach which we call dynamics-based machine learning. And here the focus is on the identifications of these key structures of the phase space, which are called spectral submanifolds. And these are, you can imagine these as being hypersurfaces into the phase space that also exist in genetic embeddings, and they are highly influential for the dynamics. They are attracting, they can capture non-linearizable phenomena, and their dynamics can be also written in very simple normal forms that have physical meaning, and normal forms are really the core of nonlinear dynamics. And capitalizing on these structures, we developed a code, and also we tested it on experimental data and also numerical simulations data, and this is all open source in the sharing policies that was envisioned before. So both code and data are available for this. And if you want more details, you can talk to me later or check our papers eventually, but I want to show you here some results. And the first one I want to show you is basically liquid sloshing of a water tank. And as you see here, it's pretty complex motion of the fluid which is undergoing. And what we are observing here in this real experiment is just the center of mass of this water tank being moved. And by training on unforced data that you see on the top of this slide, we were able to make predictions of the force regime of the structure. So what you see in the green line does have basically a perfect agreement with the experimental validation, with experimental verifications, and we didn't see any other approach that was able to have this accuracy. Other examples that we have, and these are all publicly available, are structural dynamics, in which we were able to characterize the nonlinear properties of systems with or without resonances, but applications are also found of the same code, even from high-dimensional simulation data. You see here model reductions for an airplane wing that has over 100,000 degrees of freedom that takes ages to simulate, and we constructed a simple two-dimensional degrees of freedom that controls all the dynamics and has a very, very good accuracy with numerical simulations, or even predictions of tipping points. And this is a fundamental fluid dynamics case study, the Couette flow, that has this tipping point and transition, which is similar to what happens to the climate. And by this approach based on spectral submanifolds, we were able to predict where the dynamics was going to which state of the system. And with this, I want to thank you for your attention. And if you have any questions, I'll be happy to talk to you later. Thank you very much.